Hello, this is lecture 13B, Riemann Sums and the Riemann Integral for Calculus 1. My name is Scott Grizzard from the University of South Florida. So last time we talked about antiderivatives, and then we finished talking about, in part 2 of last time, we talked about the min and max functions. Today what we're going to do is use the idea of the min-max functions to build the definition of the integral, and then look at the normal mainstream notation for this area under the curve, which is the integral symbol, and where that comes from. We're going to talk about the death of Archimedes. We're going to talk about Riemann sums, the formal definition of the Riemann integral, and then a bunch of notation. And of course, we'll do some computations and stuff like that. Our context, remember that our context right now is the fundamental theorem of calculus. That's what module 4 is all about. So remember that if f is continuous on D and G is some antiderivative of f, then the derivative of the area under the curve function is simply f. And if we have the area under the curve for f from a to x is g of x minus g of a, where g was some antiderivative of f. So that's the context. And what we need in order to prove this is a very rigorous definition of the area under the curve. So that's what we're going to do. All right. So the big idea, what I'm going to do is I'm going to fix x at a certain point. And we did the same thing when we defined the derivative. Remember this. We fixed the x, and then we had f prime of x be the limit of the secant line estimates. And we're going to do something very similar with the integral with the area under the curve function now. The big thing, and this is a big thing, don't get I keep making this point in that calculus, things are, a lot of things are simple, but hard. The notation for this thing is complicated, and hard. So don't lose the forest for the trees, okay? Remember, I want to think of the big picture, okay? Okay, so last time I talked about the min and max function. So remember that the minimum is going to be here. I'm defining the minimum, fa of x, to be the minimum of, if x is greater than a, if I'm right at my base point, it's the minimum, the lowest y value between a and x. And if x is less than, then it's the lowest y value between x and a. So I have these two functions, min and max. And I would refer you to the last lecture if you find that confusing. And of course, please ask me questions as you wish. Max was defined the same way. So what we're going to do today is talk about how we define, we're going to use this to define the area under the curve in a very specific way. And this all goes back to Archimedes. And Archimedes died in 211 BCE. And this thing is named after Riemann, who died in 1866. So bear in mind that Archimedes had kind of figured this out, and it took 2,000 years for the rest of the world to catch up to what Archimedes was talking about. So this was the idea, just the big idea that Archimedes had. Now, Archimedes was dealing with circles and things like that. And bear in mind that he didn't have this nice Cartesian system that we now have. So Archimedes' idea was that I could take a shape like a circle, okay? And then I could fill it with things that I could measure. So he might not have like the area of a circle or the area of an ellipse, but he could fill it with, say, a square here, and then a square here. And you could compute all of these shapes here. So you could come up with, this was his idea of exhaustion. You could come up with an area that you could compute that was always smaller. And then you could also do the exact same thing on the outside by coming up with shapes that were always bigger. And if he didn't really have a concept of a limit, but if the things the smaller pieces, okay, if you, as you added more and more pieces on the smaller end, and as you took away more and more pieces on the larger end, so if I take this big square and then I subtract those 4 squares and then I subtract all these things, I would actually come up with the area of the figure that was enclosed. Okay? So that was kind of his idea. 2,000 years later, Riemann came up with a way of saying what he wanted to say. And that's to say, this idea that what I could do is I could take a whole bunch of rectangles that were always smaller. This is a half circle. I could come up with rectangles that were always smaller than the figure I wanted to map out. And then I could look at rectangles that were bigger than the area that I was trying to map out. And if all of these numbers, if these two things headed to the same place, then I would have the area of, if I took the limit, and again, Archimedes didn't have the formal notion of a limit that we do now, but if I took the limit of these small rectangles, I would get the thing. So, this is actually how Archimedes died. So, Archimedes was hanging out in Syracuse, and remember that he's this is 211 BCE, and the Romans are invading Syracuse, and Archimedes is giving them lots of trouble, and the Romans want him alive. So they send a centurion to capture Archimedes, just as the Romans are finally getting through the walls. And Archimedes has been doing things to kill Romans by coming up with engineering things. So they want to capture Archimedes. So the Roman comes in and he's all, Archimedes, vide, vide, Archimedes is sitting there studying, and he's looking at this thing, and he goes, vide, 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 rectangulum infinitati, rectangulum infinitati, rectangulum tiny, vide, lottie, 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 rectangulum infinitati, lottie, 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 lottie. Lottie, 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 lottie. Lottie, 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 rectangulum infinitati. Quond the Fuci. And he killed Archimedes. So that's how Archimedes died. But that's the point that we want to remember. We want to remember lottie, 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 rectangulum infinitati. Okay? So as I divide this thing into smaller and smaller rectangles, I'm going to wind up with the area. That's the big picture. And don't lose the big picture. It's lottie, 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 rectangulum infinitati. Now let's get into specifics. Okay? Here I have the function f of x equals x cubed minus 3x squared plus 5. And I want to make an estimate from 0 to 2. So right now I'm going to do 2 rectangles, and what I want is the lower estimate with 2 rectangles. So what I'm going to do is I'm going to measure this thing. So the width of each rectangle is 1. The height of each rectangle, of this first rectangle, so I want an underestimate. So this first rectangle, this is where, f of 1 is smaller than f of 0 and anything between. So I go up here to the minimum, right? So what I'm going to do is I'm going to get the minimum point between 0 and 1. Okay? I take the minimum of f01 plus the min of f1 of 2. So I want the smallest thing here, that's the height of the first rectangle, times 1, which is the width, times 1, which is the width. Okay, so this right here, the height equals 3. And this height right here is 1. And then the width of each rectangle here, I'm going 2 spots from 0 to 2. So the width is 1 each. So when I add together this height here, which is 3, times its width 1, plus the height here, which is 1, plus 1 here. I get 3 plus 1, and that equals 4. So my lower estimate of this function here is 4. With 2 rectangles. Well, now I'm going to go to 4 rectangles, and I do the same thing. Well, this is 4 rectangles, and I want the lower. So I take the min, the width now, I've got 2 as my total width because I'm going from 0 to 2. If I want to do 4 rectangles, I'm going to take the min here times 0.5, which is the width, plus the min here. The height of this rectangle is min f of 0.5 to 1 times the width, which is 0.5. I got the min here, which is about 1.6-ish, times 0.5. And then I've got 1.5. So I add those up together, and I wind up with 5. So 4 here is my first underestimate. I double the number of rectangles I have. I get 5. But what I want is a whole lot of these. So what I'm going to do, I wanted to start with 2 rectangles, and there are those 2 rectangles I just set, okay, where I get 4 as my estimate. Okay. Well, that means I've got 2 rectangles. I added this area and this area here, and I get 4. Now I want to increase the number of rectangles to 4. And that's going to give me that estimate of 5, which I was saying before. Okay. I add this one, this one, this one, and this one. Well, I can keep going. Here is 8 rectangles, and I'm going to get 5.5 as my estimate. But again, lottie, rectangulum infinitati. So if I go up to 32 rectangles, I wind up with 5.87. Okay, well, 32 rectangles is not an infinite number of rectangles. So let's do a couple more. Here I include, there's my 32 rectangles. I keep going. So my rectangles are getting smaller and smaller and smaller. Here I've got 512 rectangles, and I've got 5.99 as my estimate. Again, I could go, this one right here is always over estimates. So now I'm going to use the upper rectangles. Oops. But notice here I have upper rectangles instead of lower rectangles. So now I'm using the max instead of the min. So at 4, if I'm using 4 rectangles, my overestimate is going to be 7. And notice here my endpoints are 0. My rectangles go from 0 to 0.5. So now my width is 0.5. I go again. I'm going to double the number of rectangles. Now I'm using 8 rectangles. Each one is 0.25 in width. And my estimate goes to 6.5. And I do this again and again and again. And at 512 rectangles, I wind up with 6.007, blah, blah, blah. So again, lottie, rectangulum infinitati. Lottie, rectangulum infinitati. So if I do this, it's pretty clear that these numbers, these limits are heading to 6, right? My underestimate is at 512 rectangles is 5.99. My overestimate at 512 rectangles is 6.007. Both of these things are heading to 6. Okay. So the question is, how do I write? I want to write the formula for n rectangles. Okay. So here I had 4 rectangles and I summed them up. Okay, well, let's see. How did I do it for 4 rectangles? My total width for the whole thing was 2. And then I wanted to subdivide, so I went from my rightmost endpoint, my x at the end was 2, and my base point was 0. And then I divided that into 4 rectangles, giving me each one a width of 0.5. So now there's my base point. Now I need to be able to compute where those are. I need to be able to make an expression for the height. And I need to be able to make an expression for each width. So that's the goal. Okay. I need the width of each rectangle and the height of each rectangle. For width, I need to subdivide a to x into n pieces. So if n equals 4, my pieces are going to be 0, 0.5, 1, and 1.5. The length of 2 divided by the 4. Now, suppose a was 1 and x was 5. That would give me 5 minus 1 over n. Okay. So my width of each rectangle, is the endpoint x. This is the upper endpoint. There's my base point, and this is my number right here of rectangles. So my change in t, or change in x, if you're looking at the book, is going to be x minus a all over n. Okay. Now, that gives me the change in t. That's my change. Now, height. Well, to do this, I need endpoints for each rectangle in the x space. For the lower rectangle, I'm going to use the min of f from tn minus 1 to t naught. So let's go back here and label these. Instead of labeling them with x, let's label them with t's like we are here. So this right here is t0. This right here is t1. This right here is t2. And t4 here, I've only got 4 rectangles, equals x. Well, here I'm going to have tn equal x. Right? So I've got t naught, t1, t2, t3, t4, t5. And each one is going to be separated by change in x. So t0 is going to equal a, and tn is going to equal tn minus 1 plus the change in t. So I've recursively defined each one of these. So again, and then what I'm going to do is sum them. So I'm going to combine the height and the width. And for the lower rectangle, I'm going to have the change in t times so this right here is the width. And this is the height of the first rectangle, plus the width and the height of the second rectangle, plus blah, 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 blah. And then I'm going to go to the nth rectangle, which is going to be f of the minimum from f of tn minus 1 to tn. So if we look at this equation here, back at our example, here's our lower rectangles. So each one of these, I'm going to go from 0 to 0.25. I want the minimum at that, which is that height there. Here I want the minimum. There I want the minimum. There I want the minimum. Here's a different example. Here's my 4 rectangles. Here my equation's a little different. And now I'm looking at 4 rectangles. This one here goes from, the total thing is from -2 to 2. This is the first rectangle. This is the second. This is the third. And this is the fourth. So for my 4 rectangles, the lowest point here is the one at -1. The lowest point here is f of 0. The lowest point between 0 and 1 is again f of 0 at 0.5. And the lowest point here is at f of 1. And again, I want lottie, 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 rectangulum infinitati. So if I do 16 rectangles, the first rectangle, the width is going to go from -2. Now the total here is 4. So 4 over 16 is 1/4. That's my change in t here. Okay. So if I wanted to go ahead and copy this, okay, here, right here, this is A, which equals T naught. This is T1. Right? I've got 16 rectangles. So that's my change in T. I've got 16 rectangles here, which is going to give me 1/4 as my change in T. t0, which equals a, equals -2. And then t1 equals t0 plus 1/4, which equals -1.75. t2 equals t1 plus 1/4, which equals t1 was -1.75, so this is going to be -1.5. t3 is going to equal t2 plus 0.25, which is going to equal -1.25, and so on and so on and so forth. Right, so that's going to be the height of that first rectangle. Okay. And so on and so on and so forth. Okay, so that's how this definition works. Again, don't lose the forest for the trees. Remember, a lottie, rectangulum infinitati. Okay. So what I'm going to do is I'm going to use this sigma signal. Right, so what I'm doing is summing. Now, I don't know if you remember this from pre-calc, but this symbol right here means sum. So this right here, I've got t0 to t1. So what I'm going to do is I'm going to start k at 1, and I'm going to go back 1 to t0, right? So I don't have a k equals 0 term, so this is going to give me the min f of tk minus 1. Well, if k is 1, this gives me t0 to t1 times change in t. Plus, now I let k equal 2. I'm going to get the minimum. The height here is going to be t, is going to be this one when t equals 2. Then it's going to be this one when t equals 3. Blah, 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 blah. And at the last one, when k equals n, I'm going to have this term. Okay. And then these are the definitions right here where the change in t equals x minus a over n. t0 equals a, and tk equals tk minus 1 plus change in t. So this is going to give me my lower sum for n rectangles. This is going to give me my upper sum for n rectangles. Now, if as I go to infinity, if the limit as n goes to infinity of the lower equals the n goes to infinity of the upper, then I'm going to say that the area under the curve of f from a to x equals the limit as n goes to infinity of the lower sum or the upper sum. It doesn't matter because they're equal. And that there gives me a formal definition for the area under the curve. Okay. Now, I'm going to introduce some new notation here. Notice that what I have here is a sum. So when we did the derivative, right, we had this change in y over a change in x. And then I took the limit as the change in x went to 0. And I wound up with this as the symbol. Right? So this was Greek and this was Latin characters. Right? That was the derivative. For area, I have here the limit. I have the limit as n goes to infinity of this sum here. Right? That's what that means. Well, this right here is Greek. That right there is Greek. And what I'm going to do is go to Latin. So I'm going to make this weird S symbol. That's what that is. It's an S. I'm going to put the lower limit here. I'm going to put the upper limit up here. And then I'm going to put the Latin D instead of the Greek delta. So that's our new notation. This is integral notation. Okay? My integral notation is that I'm going to take the base point here, the upper point here, the x, and I've got f of t dt. And then I've got this theorem. And the theorem says that if f is continuous on AB, then f is always going to have the Riemann integral. Okay, the area under the curve is well defined under this concept because the limit as n goes to infinity of the lower equals the limit as n goes to infinity of the upper. So if f is continuous, then it doesn't matter which one you use, and that's the idea of this thing. So in other words, what I'm saying is that this holds if f is continuous, always. If f is continuous, things are happy. Okay, well, that's all well and good. I've got this conceptual idea of upper and lower limits. And that is going to give me this very nice things when I want to do theorems. Well, if we wanted to do this faster with a computer, what we're going to do is we're going to use left and right endpoints. Okay? So when it comes down to computing them, we want to use left and right instead of upper and lower. And let me show you what I mean by that. Okay. So if I want to use right endpoints, when dealing with, instead of dealing with min and max, I'm just going to use f of tk as the height for each rectangle. If I want left endpoints, I'm going to use f of tk minus 1. So let me show you what that's going to look like. Let's say what I want to do is I want to compute the Riemann sum for left endpoints on cosine of x plus 1 over the interval negative pi to pi. So my first rectangle, I want to use left endpoints. So if I use a left endpoint, I'm going to use this one. And then I'm going to go over here, and I'm going to have no height, because f of t0 equals 0. Right. I plug in negative pi into this equation, and I wind up with 0, because I'll wind up with the cosine of negative pi, which is negative 1. That's my eastiness at negative pi, plus 1, which is 0. Now I'm going to have a left rectangle here. This is f of t1, and t1 is negative pi over 2. So the height of that rectangle is going to be 1. The height of this rectangle, I just go to the left and go up 2. The height of this rectangle, and then I go right here to this rectangle. So I've got 4 rectangles, this one with no height, this one here with a height of 1, this one here with a height of 2, and this one here with another height of 1. And that's how I work with left rectangles. And I could do the same thing with right rectangles, except going the other direction. Now, my change in t, I've got 4 rectangles. My change in t is pi over 2. So my left 4 rectangles is going to be f of negative pi times pi over 2, width times height, height times width, height times width, height times width. So I'm going to get 0 times pi over 2 plus 1 times pi over 2 plus 2 times pi over 2 plus 1 times pi over 2. And I'm going to wind up with 2 pi as my answer. Okay, so that's how I would compute this with left rectangles. Okay, well, now we've kind of got a way to define the integral. But part of this thing, this big theorem, is that I can define AUC using any points I want. So I'm just going to use the right points because I think they're the simplest to write. Now, you don't have to. You can use the min. You can use the max, you can use the left, or you can use the right. It's totally up to you. Define it as you want. Okay? As long as you're getting lottie, rectangulum infinitati. The book has this whole thing on partitions, the point being that you could choose midpoints. You could choose, points anywhere in the middle as long as you have a lottie of rectangulum infinitati. Okay. So here I'm going to use right rectangles, and that's going to give me the limit as n goes to infinity of the sum of k equals 1 to n of f of tk times change in t. And I have to actually define these terms. So I have to say change in t is x minus a over n, t naught equals a, and tk equals tk minus 1 plus, this is incorrect, that should be change in t. Right, so each one I go up. I'm defining this recursively, right? I've got t naught equals a, and then for any k greater than 0, I've got tk equals tk minus 1 plus change in t. So I'm using integral notation here. I've got the integral from a to x, f of t dt equals the limit as n goes to infinity of this term here. Now, I didn't have to use that. I could have used left. I could have used right. I could have used upper. I could have used lower. Okay? I can also, if I solve this recursion, I'm going to wind up with a plus k times change in t. And do that on your own. So solve the recursion. If I have... So you can solve that recursive formula if you remember how to do that. That was covered in pre-calc. And if you do that, you'll get this. But I don't care. You can use this formula, or you can use this pair of formulas. I actually like this pair better, but you can use either one. Okay. And the point is, if f is continuous, it doesn't matter which one you use. It just doesn't matter. Okay. So you can use left, upper, lower, any one you want. Okay, so what are the big ideas? Lottie, 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 rectangulum infinitati. Lots and lots and lots of really small rectangles. For computations, it's usually easier to use left and right. For proofs, you really want to use the upper and lower definitions. And when we prove fundamental theorem of calculus, we're going to use the upper and lower definitions. If f is continuous, it doesn't matter which ones you use. For the definition of the Riemann integral, I'm going to fix x, make little rectangles, add the rectangles, and then take the limit as n goes to infinity, right? So I take the limit as my rectangles go to infinity. So again, a lottie, 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 rectangulum infinitati. That's all what I have for you today. Good evening, everyone, and I'll see you next time.